See, last time we have talked about how to expand a function using Maclaurin series. So I think you might have gone through these examples. Let us once try to revisit these questions. So you can see you are required to show that e raised to z upon z square happens to be this when z is non-zero. Basically, e raised to z is the entire. Entire means it is analytic everywhere in the complex plane. So we can expand e raised to z using Maclaurin series. You know what is Maclaurin series? It is summation n running from 0 to infinity an times z raised to n. And how to calculate an? Means the coefficient of z raised to n. It is the nth derivative of f at 0 upon n factorial. So it is an z raised to n. So going back to our function e raised to z, its nth derivative is e raised to z itself. So whenever we calculate its value at 0, it becomes e raised to 0, which equals 1. So if I now put the value of nth derivative in this summation, we get this to be 1 by n factorial times z raised to n, and summation running from 0 to infinity. Meaning thereby it will be 1 plus z square by 2 factorial and so on. Now, for non-zero z, I can divide by z. So we are dividing here by z square. So what it becomes? 1 by z square times this summation. When this summation is expanded, you can see this is like this. Outside multiplied by 1 by z square, and it gives us the value 1 by z square plus 1 by z. 1 z is getting cancelled. Next, z square gets cancelled and we are left with 1 by 2 factorial plus 1 z is left in the numerator. So it is z upon 3 factorial plus z square upon 4 factorial plus and so on. So whenever you are required to expand this way, first you confirm whether your function is analytic within that domain or not where you are trying. In this case, they are asking you for non-zero z, means only except origin throughout the plane except the origin. So that is what we have done. I hope the thing is clear to you. I would like to proceed with this. The second question was expansion of sine of z square upon z raised to 4 at non-zero z. So we know sine z is again an entire function. What I mean by entire function? A function should be analytic at each and every point in the complex plane. So sine z is an entire function. By Maclaurin series, we can expand our sine z as what? Summation n running from 0 to infinity minus 1 raised to n, meaning alternate plus minus sign. Z raised to 2n plus 1 means odd powers of z upon 2n plus 1 factorial. Same factorial we are having in the denominator. Now we want to find out sine of z square. So it's we are replacing z by z square. So we replace z by z square and the output is this one. We know laws of indices, twice of 2n plus 1 will give us 4n plus 2. And once we expand it, put the values of n starting from 0 onwards, we will get this series. Now, this is valid throughout in the complex plane. Now for non-zero z, now we are coming to z not equal to 0. Why? Because we are dividing by z. So this series, let us divide by z raised to 4 as the question demands. So what we get is 1 by z raised to 4 times this whole, and once I expand it, what do I get? You can check. Z raised to 4 when divides to z square, we naturally will have 1 upon z square. This is our first term. Now minus. We divide by z raised to 4, it is going to give us z square in the denominator. Numerator is 1 and there was 3 factorial here. So 1 by 3 factorial times z square in the denominator. Plus sign doesn't matter. So plus what we are having is z raised to 10 upon 5 factorial divided by z raised to 4. So what it will be? 1 by 5 factorial and obviously z raised to 6. Then there is minus sign. Z raised to 14 upon z raised to 4. So we'll have z raised to 10 in the denominator. There is 7 factorial here and numerator is 1 plus and so on. So this was expected and we have reached to the same. So I hope that
Madam,
is
raised to
very
minus 8, no?
raised to minus 10 in the numerator. So when it goes down, it becomes z raised to plus 10. Z
Okay.
raised to 14 was in the numerator. When it goes down, it becomes plus 10, isn't it?
Hmm.
Okay. So I hope the thing is very clear to you. Is it?
Yes, ma'am.
Just I take a pause for a few minutes. I Now let us move to the next question. I think these questions are quite now familiar to you. Do you have any doubt?
Yes, madam.
Anywhere do you have any doubt?
No, madam.
No, no? And how to make it
Mhm.
back using summation sign? Have you got this? So let's have an overview. Talking about sin hz upon z square. So everywhere what you find, our function is upon power of z. So up till now we were handling entire functions and we used to divide them by z for non-zero z. Is it fine? And there what we observe is there are few negative powers of z and some are positive powers of z. So I think you might have observed this. In this case also, we are getting, you can see, In this case, you can see the negative powers of z, there is a single term, and rest all, they are positive powers of z. So every time we will be meeting the same fact. Here also you are watching, if I multiply by z cube to cos h of 1 by z, we are getting z by 2 plus z cube. Positive powers are only 2, whereas negative powers are infinitely many. In this case, we are having negative power of z only once, whereas positive powers are infinitely many. Have you observed this?
Yes, ma'am.
Yeah, and that is actually needed to define residue and poles. So we'll go to that later, but I think at this particular moment, you are able to expand such kind of things. Have you got the expansions? There was,
Yes, madam.
yeah, there is hyperbolic cos of 1 by z that you expanded this way and just multiplied by z cube, and that is
Hmm.
giving you only two positive terms. I mean, two positive indices of z, and rest all are negative powers of z. It is an ending to
Hmm.
this side. Okay. Then we move
Yes.
to, see, here we are saying all z's such that mod z lies between 0 to 4. Means what? Mod z is not a 0. When mod z is 0, it is only at the origin. So we are excluding origin. And what about this? Mod z less than 4, it's a disk centered at the origin and of radius maximum 4,
Oh,
boundary is not taken. If it would have been less or equal, we would have taken the boundary. Okay, excluding the circumference
yes.
and excluding the center. So such kind of thing we refer to as annulus. What is this? This is an annulus. And in the annulus, they are asking you to expand this. So let us say, how do we do this? We went back to the function. We have taken z common. While taking z common, we have taken this 4 also common. Why for? Because we want the thing to be 1 minus something. And that something should have modulus less than 1. That is the expansion. We have already seen the series. If at all you are having 1 upon, there we used to call it as a z, let us call it as omega for the time being. So 1 by omega, I'm sorry, 1 minus omega, isn't it? If it happens to be 1 upon 1 minus omega, how do we write it? 1 plus omega. Do you agree? I hope you remember this. Plus omega
Yes,
square
madam.
Yes,
plus
ma'am.
and so on. What was this? This was summation omega raised to n and runs from 0 to infinity. Is it fine?
Yes.
Yeah.
Okay.
So that is what we have thought of, and the same kind of thing. But when this happens, only if mod of this omega is less than 1. Only if mod of omega is less than 1. That is why we are taking care of this particular condition. Mod z is less than 4. So what will happen to mod z upon 4? It will be less than 1. And then we can expand it. And that is why we want z by 4. And for that we have taken this 4z common. Fine?
Okay. Huh.
Okay. Now, I would like to clear this. And okay, will do. Now, we have taken this 4z out, and actually now we are worried about what? 1 upon 1 minus z by 4, only this particular. So we will expand it. This is the expansion. Just now we wrote it. It will be just powers of z by 4. Fine. This is the ready-made expansion, we know.
Yes.
Whenever mod of z by 4 is less than 1, we'll have this expansion. This is very direct. Now you multiply it outside by 4z. If you multiply it outside by 4z, what happens is this. And I hope you got it. 1 by 4z out. This z will get cancelled and this will be 4 square. Then 1z is getting cancelled. You are left with 1z here. And this is 4 into 4 square. So 4 cube. Then you'll have z square here and 4 raised to 4 and so on. So this was just the thing they asked you to prove. Then you just summarize it as a summation sign. Fine?
Madam.
Now, I would like to move to the next page, and here we introduce Laurent series. What this Laurent series tells you? There is a difference between Taylor's and Laurent's. Taylor talks about within a disk, and Laurent talks about the space between two disks. He talks about the space between two disks. I would like to just point it out to you. I'm having R1 as one radius, R2 as another radius, so there will be something like this, and outside I'll be having this kind of space, and we will be referring space between these two, space between these two, such kind of thing, the thing that I'm shading. You can see it is within two disks, enclosed between two disks. Earlier disk has, the smaller disk has a radius R1, the bigger one is having radius R2, and the center is at Z0. The point is within the circles. This point is Z0 point. I feel you are getting. So within this particular shaded region means between two disks. Now F should be analytic in this annular region. Now, if C denotes a positively oriented simple closed contour around Z0 lying in that domain, then at each point in the domain, f of z has series representation. And what is the series representation you see? I hope you can see it. Am I properly audible to you?
Yes, madam.
Okay, I would like to use annotation then. You can see an. If I put n equal to 0, it becomes a naught. And z minus z naught raised to 0 makes it 1. Next term will be, if I put 1, it is a1 z minus z naught raised to 1 plus a2 times z minus z naught bracket square, and so on. I think there is no issue with the positive powers. The issue comes when I talk about negative powers. It is now n equal to 1. So this is going to be b1 and divided by z minus z naught raised to 1. Followed me? To this side. If I put n equal to 2, this becomes b2 upon z minus z naught bracket square, and so on. This also continues to infinity. This is up to infinity, this is also up to infinity. So this kind of representation is given by Laurent. Followed the thing?
Yes, madam.
Yeah. So the Laurent's expansion actually talks about within annular domain, and the powers of z minus z naught, they extend from minus infinity to plus infinity. So this is what we mean by this particular. All right. I would like to go back. Now let us deal about the Laurent series for various functions. Now again we are meeting with the same kind of function. There is sine of 1 by z square. If it happens to be sine of z, then I can say it is entire. But when 1 by z comes in picture, we have to exclude this 0, and that is why it becomes annulus. That is why we are saying 0 less than mod z less than infinity. Actually, we are taking the whole complex plane, but we are excluding the origin. Followed me? We are excluding
Yes.
the origin. So this is annular region. And within this annular region, again our sign is with 1 by z square, it is entire. And now you can see sine of 1 by z square. I can expand this way. I just replaced rz by 1 upon z square. So we know the representation of sine z. What is it? Summation and running from 0 to infinity minus 1 raised to n upon 2n plus 1 factorial is a
Minus
common
1.
thing. Yes, and there was z raised to
Oh.
2n plus 1, which is now replaced by 1 upon z
Mhm.
square raised to 2n plus 1. Fine. And with the laws of
Yes.
indices, directly you come to this. So I hope there is nothing. And once you expand it, what you find? If I put n equal to 0, I'll get 1 by z square. If I put n equal to 1, I'll be getting z raised to 6 and so on. So I think calculation is quite easy. And then just multiply by z square,
Yes, ma'am.
which takes you to this kind of thing. Now, if you want to enclose it within summation sign, this one has actually a different thing. If I observe this is z raised to 4, z raised to 8, z raised to 12, they are all powers, I mean multiples of 4. So I can engage it as z raised to
4.
10. Is it? And that is why we will
Yes.
begin with n equal to 1. Again, one more thing I find, if I put n equal to 1, this is 3 factorial, so I can read it as 2n plus 1. If I go to 5 factorial, again it becomes 2 2s are 4 plus 1, 5 factorial. If I go to 7, again I can accommodate it as what? 3 2s are plus 1. So that is the thing we have taken care of. So we begin our summation from n equal to 1 to infinity. Followed me?
Yes, ma'am.
Yeah. So this is the actual expansion of this particular kind of function. So this is Laurent series expansion. Why Laurent's? Because Taylor doesn't accommodate the negative powers of z. Here all are negative powers of z. So it is Laurent series. And one more thing is, because we are dealing with the annulus, Taylor deals only with the disk and Laurent deals with the annulus. What me?
Yeah, ma'am.
Now, again they are asking you to derive the Laurent series representation for this. So e raised to z you can expand and then take care of this 1 upon z plus 1 bracket square. But because there is z plus 1, we should talk in the same language. This is z plus 1. So the e raised to z also I should talk in the same language. So I can write e raised to z as what? How would you express e raised to z? E raised to z plus 1 minus 1, and that minus 1 I can say is upon e. Will it do?
Okay.
So that is the thing we need. Okay, one. So you can watch the expansion here. what I have done is simply I have written it as e raised to z plus 1 upon e. We expanded it and simply multiplied outside by 1 by e. That is the thing. I hope it is quite simple. And there too, what we have done, the positive powers of z plus 1 we have taken aside within summation, and we are taking a separate space for 1 upon z plus 1 kind of thing. So hope you are following this. Is it
Yes, ma'am.
fine? Okay. Now talking of 1 upon 1 plus z kind of thing. When it happens to be 1 upon 1 plus z, it is actually a must for me to see what is the region where I'm expanding it. So what they have given us, we can check it. They have given us to expand it in 1 less than mod z less than infinity. So what to do now? So if I take it to be 1 upon z, then what will happen? If I go to 1 upon z, then surely its modulus will be less than 1. Are you getting me? This actually means 1 by mod z less than 1. Is it fine? From here I went here.
Hmm.
1 by mod z is less than 1. So we are taking care of this 1 by z kind of thing. So what we'll do is, we'll convert this 1 upon 1 plus z as 1 by z times 1 upon 1 plus 1 by z. Okay? Now you expand this 1 plus 1 by z.
Oh,
But you know simply the formula for 1 minus kind of thing. So that you have to take care of. So let us go to that. Here you can see it very clearly. This is 1 less than mod z less than infinity. So we are saying mod of 1 by z is less than 1 and z is non-zero. Why z is non-zero? Because you are saying your z is greater than this one. Modulus of z is greater than 1 when you say how can z be 0? ज्या z चा मॉड्युलस 1 पेक्षा मोठा आहे तो z 0 असेल का?
nine.
So z is non-zero. I have just mentioned this for you. Once you say 1 by mod z, 1 by z has mod less than 1, but my mod z is greater than 1, will mean that z is non-zero. Now you can apply Maclaurin series. What is the expansion? So again we have to go with this. What you can say, 1 upon 1 minus omega
Hmm.
is summation omega raised to n. I feel all of you know this. Once
Yes.
we are saying this being 1 plus, how should I write it? 1 upon 1 minus 1 by z. Can I say so?
Hmm.
So naturally this will be powers of minus 1 by z.
Minus.
Being powers of minus 1 by z, it becomes minus 1 raised to n upon z raised to n. Is it fine?
Yes, ma'am.
Yeah, and rest things become very clear then. There is nothing. So this is so 1 by z you are multiplying out, so you can take it within the summation. It becomes z raised to n plus 1. Because you are beginning with n with 0, how would you change it? You can make it into, because if you want z raised to n, then you have to replace n by n minus 1. If I replace my n by n minus 1, what will happen? Everywhere I'll put n as n minus 1. So naturally n minus 1 equal to 0. So n will begin with 1. If I replace in this place n minus 1, there was plus 1 also. So it will go to z raised to n. Are you following me? And this n should be written as n minus 1. I hope you agree.
Yes, ma'am.
Yeah. So if you call it as n minus 1 will do, or if you call it as n plus 1, still it takes the same kind of thing, because there is a difference of 2 within minus 1 and plus 1. And actually minus raised to even and minus raised to odd, two odds differ by 2, two evens differ by 2. So either you call it as minus 1 or plus 1, actually the thing obeys. Are you following me? So either I
Yes,
call
ma'am.
it as n minus 1 or n plus 1, it will play the same effect. You can expand it and check.
Hmm.
Now, I would like to move ahead with this question, which is quite important for us, because this was asked in the exam in our previous question papers. What is the question? Let us see. Give two Laurent series expansions in powers of z for the function. And what is the function? 1 upon z square times 1 minus z. So what do you observe? Z square is in the denominator. So if I put z equal to 0, there is a problem. For z equal to 0, there is a problem. So 0 cannot be included. And talking of
One
this
per month.
1 minus z equal to 1 creates
Hmm.
a problem. Elsewhere in the complex plane, there is no problem. There is a problem only with z equal to 0 and z equal to 1.
Yeah.
So
One.
in our plane, there are only 2 points, z equal to 0 and z equal to 1. The rest of the points, they are okay for us. So what we'll do? We will take unit circle round is 0, such that mod z is less than 1. So z will just touch this, which is not within, which is not an interior point, and the remaining plane with mod z greater than 1. Another thing will be 1 less than mod z less than infinity, which includes the rest of the points. Are you getting me? We will be
Yes,
talking
ma'am.
about only two regions: disk, unit disk, and outside. Unit disk and outside. So this will be the thing we will be dealing with. Okay. I would like you to rejoin me.